Welcome students. This lecture is a part of lecture series for third semester students. This lecture is about the concepts of the course entitled as Digital Electronics and Logic Design, having course code ECE 313D. Here are the contents that I will discuss in this lecture. First is logic gates. Before considering this topic of logic gates, let me tell you one thing, that in this lecture the binary numbers 0 and 1 are actually used to represent some logic. That is, logic 0 represents false statement, or I may say a low level voltage, and logic 1 represents true statement, or I may say a high level voltage. Actually, there are some concepts of positive and negative logic that I will discuss in next lecture. Right now, let us concentrate on the topic, that is logic gates. Logic gates are basically the building blocks of a digital circuit. They are actually the electronic circuits that are able to operate on a number of binary inputs in order to perform a particular logic function. Each gate has its symbol, truth table, and logical expression. Truth table indicates output for different possible combinations of input, and logical expression, or I may say the Boolean expression, designates the relationship between the input and the output variables. These are the gates that we are going to study in this lecture. First, it is the NOT gate. NOT gate actually performs a basic logical operation called as inversion or complementation. It inverts the input. That is, if the input is 1, output will be 0. If the input is 0, output will be 1. This you can see from this truth table, that is, whatever is the input, the output is the opposite of the input. So NOT gate is referred as an inverter. This is the symbol of NOT gate, and this is its expression, that is, output is equivalent to input with a bar, that is A complement, input complement. Next, it is AND gate. AND gate performs the operation which is called as AND operation, and this operation resembles multiplication process. Its expression is given here, that is, C is output and A and B are two inputs, A dot B. Further, AND gate can have an input and one output, where n can be greater or equivalent to 2. But here we have taken n is equivalent to 2, that is, we have taken only two inputs, so it's A and B. This is the AND gate, this is the output. Further, this is the truth table of the AND gate, which has been formed by considering different combinations of input. Like here we have got two inputs, then 2 raised power 2 is 4, so we will have 4 combinations, that is 0 0 0 1 1 0 1 1. After that, output is calculated from this expression. It is 0.0 is 0, 0.1 is 0, 1.0 is 0, and 1.1 is 1. Some conclusive remarks can be drawn from this truth table, these which are: when both the inputs are 1, that is A and B both are 1, then output is logic 1. Okay. Another remark is that if any of the input is 0, like here it is 0, it is 0, and it is 0, then output is logic 0. Like it is 0 0 and 0 in these three cases. So this is the truth table of AND gate. Next it is OR gate. OR gate performs logical OR operation which somehow resembles the addition process, exceptionally a case where A is equivalent to B is equivalent to 1. That is, this is the Boolean expression, that is output will be equivalent to A plus B. Okay, like AND gate, OR gate can have an input where n is greater or equal to 2 and one output. This is the symbol of OR gate. These are the two inputs that we have considered. N is equal to 2 here. This is the output. Truth table is formed by considering the different combinations of input, and it is C is then calculated from this expression. It is 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1. This is the exceptional case, that is 1 plus 1, it is 1, not 0. This is because here ones and zeros represent logics. These are not mere bits, that is 1 bit plus 1 bit will be equal to 0 with a carry of 1. No, these are actually logics. It is logic 1 or logic 1 is equivalent to logic 1. This concept is very important here. Further, the important conclusive remark that can be drawn from this truth table is given here. It is if both the input values are 0 like here, then output value is also 0 like this, otherwise the output is 1. It's just a simple conclusive remark from this truth table. Important is symbol, truth table and Boolean expression. Next is NAND gate. NAND gate resembles AND gate, but here you can see that it is AND gate plus a small circle attached here. Therefore, we can say that NAND gate is actually not of AND gate. Not of AND gate. So, NAND operates like an AND gate followed by an inverter, like it said here. It produces the opposite results of an AND gate. Its Boolean expression is this, that is, it is A dot B is AND, and this bar makes it the expression for NAND gate. Now considering the results, if we will consider only the AND, then the results will be this, but since it is a NAND gate here, so we have to take complement of all the results, and this will form the result of A, B whole bar, that is NAND, and this will make the truth table for the NAND gate. Now a conclusive remark from this, that is if both the inputs are 0, both the inputs are 1, that is both the inputs are 1, then output is 0, otherwise the output is 1. Next is the NOR gate. NOR gate is somehow similar to OR gate except for this circle which is attached here. So we can say that NOR operates like an OR gate followed by an inverter. So its Boolean expression can be this, that is C is equivalent to A plus B, where A plus B is OR, and marking this bar over the A plus B expression makes it the expression for NOR gate. NOR gate hence produces the output which is opposite to that of the OR gate. That is, if we will see from here that A plus B, that these are the combinations of A and B, 4 combinations, and this is the result of OR, and on taking the complement of these results it will be 1 0 0 1. So this is the result of NOR, which is completely opposite to that we have obtained in OR. These 1, 2 and 3 columns will make the truth table for NOR gate. Further, if both inputs are 0, like here it's 0, then output is 1. Okay, otherwise output is 0, like here. This is just a conclusive remark drawn from the truth table, which you can make from this expression or by this table. Next, it is XOR gate. XOR gate stands for exclusive OR gate. The gate which you earlier studied, that is a simple OR gate, that gate is called as inclusive OR gate. This one is exclusive OR gate. It is symbol is given here. This is the OR gate, this part, and marking this curve here makes it XOR gate. Its Boolean expression is this, that is plus within a circle. This is the Boolean expression for the XOR gate. Further, it is also called as comparison gate because you can see from its truth table that the output is high only when the inputs are different. Hence, this gate can be used for comparison purpose, hence the name. Next is XNOR gate. XNOR gate is similar to XOR gate, like here but a circle is attached here, so it is not of XOR. So we can say that XNOR operates like an XOR gate followed by an inverter. See, this was the Boolean expression of XOR. Marking this bar over this expression makes this expression the expression for XNOR. That is, this bar makes it the expression for XNOR. Further, XNOR produces the output results of an XOR gate true because inverter has been marked. This inverter expression has been marked here, so the output will be really opposite to that of the XOR gate. That is, we had highs in case of XOR when we have the two outputs different, but here in case of XNOR, high output will be obtained when we have inputs which are same. So this point is important, that in case of XNOR, output is high only when both the inputs are same, but in case of XOR, the output is high only when the inputs are different. XNOR gate is also called as the equivalence gate, while as the XOR gate is called as comparison gate. Next, review is given here and of the different gates and their behaviors. Some switching circuits are given here which can help you to better understand the concept. It's like A and B are two switches. Further, zero state, here the zero state will represent that this switch is open, and 1 will represent that this switch is closed. So here 0 and 1 represent some logics. Now 0 0, that means both are open. When both are open, no input voltage can reach output, so Y will be 0. Again, this is 0 1, that means this will be open and this will be closed. No input voltage will reach to output, so it will be 0. Again, when this is 1, this is 0, it will be again 0. But If both are closed, that is 1 1, then input can easily reach the output and the output will be 1. So this is the truth table which resembles AND gate. So this is the switching circuit for AND gate. These are the concepts that can help you to differentiate between the concept of logics and the binary bits. Here in this lecture, 0 and 1s are the logics. Like here in NAND, NAND is represented by this form, that is A and B is written like this. This is the truth table that you can easily complement, that you can easily compare here, and you can see the results here. Next, I have again here drawn the some switching circuits of OR and NOR gate. You can see from the truth table, and you can just grasp the concepts of the switch